quantity that requires both magnitude and direction for a complete description is a vector quantity. Velocity is a vector quantity, and so is acceleration. A quantity that's completely described by magnitude is a scalar quantity. Scalars can be added, subtracted, multiplied, and divided like ordinary numbers. For example, when 3 kilograms of sand is added to 1 kilogram of cement, the resulting mixture has a mass of 4 kilograms. When 5 liters of water are poured from a pail that has 8 liters of water in it, the resulting volume is 3 liters. If a scheduled 60-minute trip has a 15-minute delay, the trip takes 75 minutes. Math involving scalar quantities is simple and straightforward. You can represent vector quantities visually by drawing arrows. The length of the arrow represents the magnitude, and the direction of the arrow represents direction. In this example, by using a scale of 1 centimeter equals 20 kilometers per hour and drawing a 3 centimeter long vector that points to the right, you represent a velocity of 60 kilometers per hour to the right. An airplane's velocity relative to the ground depends on the airplane's velocity relative to the air and on the wind's velocity. The velocity of something is often the result of combining two or more other velocities. If a small airplane is flying north at 80 kilometers per hour relative to the surrounding air, and a tailwind blows north at a velocity of 20 kilometers per hour, the plane travels 100 kilometers per hour relative to the ground below. What if the plane flies into the wind rather than with the wind? The velocity vectors are now in opposite directions. The resulting speed of the airplane is 60 kilometers per hour. Now consider an 80 km per hour airplane flying north caught in a strong crosswind of 60 km per hour blowing from west to east. The plane's speed relative to the ground can be found by adding the two vectors. The result of adding these two vectors, called the resultant, is the diagonal of the rectangle described by the two vectors. An 80 km per hour airplane flying in a 60 km per hour crosswind has a resultant speed of 100 km per hour relative to the ground. The 3-unit and 4-unit vectors at right angles add to produce a resultant vector of 5 units at 37 degrees from the horizontal. Many times we'll need to change a single vector into an equivalent set of two component vectors at right angles to each other. Any vector can be resolved into two component vectors at right angles to each other. Two vectors at right angles that add up to a given vector are known as the components of the given vector. A ball's velocity can be resolved into horizontal and vertical components. Vectors x and y are the horizontal and vertical components of a vector v.